Okay, so I want to talk about interpreting systems of differential equations geometrically. And the main tool that we have to do this is vector fields. And I want to see how this idea of eigenvectors and eigenvalues are situate themselves in vector fields. Okay, and by doing so, what we're going to be able to do is get a handle on the sort of qualitative, that is to say, not numerical, not precise mathematical statement, qualitative um, features of the solutions to these two-dimensional systems. Oh, right. And I'm going to focus on two dimensions because a lot of the complication and interest is already exhibited in two-dimensional systems. And it avoids the complication of needing to think about higher dimensional systems. Yeah. Okay. So yeah, let's take a look at uh, 2D systems and their vector fields. So real quick review. Uh, our system is going to look like x prime equals px. I'm going to think of x as being having components x1 and x2, entries x1 and x2. Remember they're functions of t generally, all right? And we construct a vector field associated with the system in the following way. At each point, which we're going to think of points as being described by vectors, displacement vectors from the origin. At each point x1, x2, which is what x is, we place a vector given by x prime equals px. Okay, so x prime is also a two-dimensional vector, and we display that information with a tiny arrow located at this point x1, x2 in the x1, x2 plane. I'm thinking of x1 as the horizontal axis, x2 as the vertical axis. Okay. This is when we do this for all points x1, x2 in the x1, x2 plane, what we get is a ocean of vectors in the plane that we call the vector field associated with the system. Okay. So, as an example, the textbook has really good pictures here. Here is an example of what I'm talking about. Ignore the red stuff. Ignore the red stuff. Just pay attention to the blue stuff. The blue stuff, that's the vector field associated with some system. I mean, I know the system. It's written here somewhere. But in any case, that is a vector field. And what we want to do is think about how eigenvectors are situated uh, in this picture. How are eigenvectors sort of displayed in a picture like this? We'll return to that picture in just a sec. But yeah, so suppose V is an eigenvector of P. With eigenvalue lambda. Okay, standard, we know this is an important element of solving this system x prime equals px is to find an eigenvector with eigenvalue and its associated eigenvalue. Okay? Then there is a line, then v, which is not zero, and maybe I'm going to emphasize that here. V is not the zero vector. So v determines a line by taking all scalar multiples of v. So I'll show you what I mean by this in just a moment. Okay, so what am I talking about? So let's say that we have here, this is the x1 axis, or that's the x2 axis actually. This is the x1 axis. This is x1 and this is x2. And let's say we have an eigenvector, non-zero. So maybe it points, I don't know what direction, it's not so terribly important, but maybe the eigenvector points in that direction for now. This is my v in purple here. Now take all scalar multiples of that vector v. And what that's going to do is stretch this vector out toward infinity, determining a line's worth of vectors, like this. Okay, and if I take negative multiples of that vector, I'm going to get the ray which emanates from the origin going in this direction. Does that make sense? Now the question is, what do vectors in the vector field look like for points that lie on this line? So this is the key idea. The vector field, the vectors in the vector field lying on this line point in the direction of the line. This should make sense, because for points along this line, x1, x2, if I feed those points to p times x, if I multiply, in other words, such points by p on the left, what I get out is lambda times that x. In other words, just a stretched version of that vector. So if I think about what the vectors look like along this line, and let's say for a moment that lambda is equal to 1 in this picture, then what's going to happen is these vectors are going to point in the same direction as the purple line, but away from the origin. Like that. Let me contrast that with the situation if lambda was negative. So let's say that we have another x1, x2 plane. But now let's say that my vector, maybe I'll draw it, well, no, I'll draw it in purple. Let's say the vector was something like this. That's my vector. And of course, scalar multiples of this vector determine a line. Something like that. And now let's suppose in this case, lambda was negative 1. Then the vectors in the vector field that lie on this purple line here will point in the same direction as the line, but now they will point toward the origin. The blue things are the vectors on in the vector field, and they point toward the origin. Because plugging such vectors which lie on the purple line, plugging those points into p times x, gives you negative x, which is the vector that points in the opposite direction. Okay? So the bottom line here, and I'll tell you what the bottom line is here. So if lambda is a positive real eigenvalue, then vectors on the line determined by the eigenvalue the eigenvector v point toward the origin along the line. In contrast, if lambda is negative but real, then the vector field points toward the... Oh, wait. Sorry, I messed up. I messed up. This shouldn't be toward. This should be away. Away from the origin along the line. If lambda is a negative real eigenvalue, then the vector field points toward the origin along the line. Okay? So on the basis of this, okay, we'll classify some systems in the next video. But we also have to talk about the complex case, okay? What happens when you have complex eigenvalues? And that's a more complicated discussion. Because we can't draw the complex eigenvectors, right? We can't draw those, at least straightforwardly, in the x1, x2 plane. Okay, see you in the next one.